Hi, welcome to another laboratory practice of semester 7, which is called Breakdown Characteristics of Oil. Perhaps you may already be familiar with the theoretical concepts behind this practical. Anyway, now let me briefly go through the content of this laboratory session. First, I am going to introduce you the main theoretical concepts you need to understand this session. For an example, what are the two categories of the insulating liquids we have, and what are the types of impurities you may encounter during this practical, and how they can affect the results of the practical. After that, I am going to conduct the laboratory session for you, and finally, I'll give you the observations of this practical, which is useful for the preparation of your lab report. Okay, without any further delay, let's move on to the theoretical concepts behind this laboratory practice. Among the insulating liquids we come across in our day-to-day life, we can identify four major categories as mineral oil, silicon, hydrocarbon, and natural esters. Each of these fluids have their own unique physical and insulating properties which determine their usage. But in this context, we are mainly focusing on the high voltage application of them. Now, let's briefly discuss how we can perform the dielectric breakdown strength test for any insulating oil in general. Here, we have to apply a potential difference to a pair of electrodes immersed in an insulating liquid. Then we can gradually increase the applied voltage, and at first we can observe a small conduction current. If the voltage is raised continuously at a critical voltage, a spark passes between the electrodes and it can be visually observed as a bright luminous path from one electrode to the other. Also, we can observe an explosive sound as a result of the impulsive pressure built through the liquid. In addition to them, in some dielectric liquids, we can observe the evolution of gas bubbles which gradually come to the surface and the formation of solid particles which are collected on the electrode surface in small pits. Okay, now we are going to talk about the two basic categories of these insulating liquids based on their level of contamination. Those are highly purified liquid dielectrics and commercial liquid dielectrics. Among these two categories, due to the insignificant or almost zero level of contamination, the highly purified liquid dielectric possess a comparatively higher dielectric strength, which is in the order of 1 megavolt per centimeter. When the previous test is performed on this type of liquids, we can observe that first, the breakdown strength has a small but definite dependence on electrode material. Second, breakdown strength decreases with the increase in electrode spacing. Third, breakdown strength depends on the hydrostatic pressure of the liquid only when they contain dissolved gases like nitrogen or oxygen. But unfortunately, these liquids are highly prone to contamination. So the commercially available insulating liquids, which may not be subjected to elaborate purifying treatments, have comparatively low breakdown strengths up to the order of 100 kilovolts per centimeter when they are used alone. In most cases, this reduction of the breakdown strengths depends upon the nature of the impurities contained than upon the nature of the liquid itself. But the effect of these impurities is relatively small for short duration voltage pulses, normally within microsecond range. Okay, now let me ask you something. Do you know what are the three basic categories of impurities contained in a liquid dielectric? Alright, now I am going to explain them briefly to you. The impurities which cause to reduce the breakdown strength of the dielectric liquids below their intrinsic strength fall into three categories. 1. dissolved gases or gas bubbles, 2. Globules of other liquids, and 3. Conducting solid particles. Now let's talk about the first category, dissolved gases or gas bubbles in brief. In general, this category of impurities consists of a lower breakdown strength than the liquid itself. So let's say there is a gas bubble appeared in between the electrodes while we apply the potential difference to the electrodes. Then there will be an internal electric field formed inside the gas bubble, and it can be given by this formula. According to that, when the external field increases, the internal field also gets increased proportionally. This causes the elongation of gas bubble in the direction of the electric field. So, when the sufficient internal field is applied, the gas inside the bubble will get breaks down. It will release some energy which can cause the decomposition of liquid molecules around that. Finally, it will lead to the total breakdown of the liquid. Okay, now let's move on to the second category of impurities, which is the globules of other liquids. This type of impurities are unstable in the applied electric field. Let's consider a spherical globule of liquid appeared in between the two electrodes. Similar to the previous case, there will be an internal electric field inside the globule, and it is given by this equation. Then the electrostatic forces cause the globule to form an elongated spheroid. When the external field increases, the internal field also gets increased, and the globule keeps on elongating. Eventually, it bridges the two electrodes, creating a low resistance path in between them. Then, at a critical value of the applied electric field, a spark goes through this low resistance path, leading the ultimate breakdown of the liquid. Now, we are going to discuss the final category of impurities, the solid impurities. We know in commercial liquids, solid impurities cannot be avoided and will be present as fibers or as dispersed solid particles. This type of impurities causes the local enhancement of the electric field. So let's see how it happens. Here I am going to consider a spherical solid particle appeared in between the electrodes. So, as a result of the externally applied electric field, there will be a force exerted on this particle, and it is given in this formula. Similarly, there can be many particles with forces exerted on them, and those forces will move the particles towards the region of strong field. Eventually, these particles will line up in the direction of the field, forming a stable chain of particles. This chain of solid impurities will distort the electric field gradually, causing a local breakdown at its critical length. This local breakdown happens at a relatively low voltage, and it leads to the complete breakdown of the dielectric liquid. So, that's all about the theoretical concepts you need to understand in this practical. Now it's time for us to move on to the laboratory session. So now let's identify the main components of this setup before starting the practical. First, you can see the step-down transformer we are using to convert the supply voltage of 230 volts into 100 volts, which then becomes the input to the oil tester. Thus, we must connect the oil tester to the 230 volts supply through this transformer. Now you can see the portable oil tester with the associated high voltage terminals. This equipment is manufactured for the withstand voltage test of hotline protectors such as insulation oil, rubber gloves, rubber high boots, and oil-contained circuit breakers. So first, take a look at the portable oil tester. As you can observe, there are two connection cords connected to this. Among them, This one is coming from the secondary side of the step down transformer and the other one is going to the high voltage terminals. What you can see on the screen now is the control board of the oil tester. Here we can identify several switches which are crucial for the tests carried out with this. First, you can observe the meter switch, which is already positioned at the transformer side. Then you can see the air circuit breaker and the main switch or the power source switch respectively. Also, there's an earth terminal on this control board. This portable oil tester can be operated in two modes as auto mode and manual mode. So the required mode can be switched using this third switch. Also, there's a voltage controller along with a voltmeter which is in kilovolt range can be observed. In addition to that, this equipment has the main transformer united with the control portion and it is used to step up the input voltage of 100 volts to 50 kilovolts. So these are the two high voltage terminals used in this setup. The output voltage of 50 kilovolts coming from the oil tester becomes the input to these terminals. Also you can see they are named as U and V. Additionally, there is an earth discharging rod to discharge these terminals whenever required. Apart from them, we are using a transparent oil cup which contains two spherical electrodes and a micrometer screw gauge to adjust the electrode gap settings. Also, we need a small funnel to pour the oil properly and a glass rod to remove gas bubbles and solid impurities from the oil. So now, let's move on to the laboratory session. Okay, here at first you can see the earth discharging rod which is in grey color by near the wall, and this is our step down transformer which is converting 230 volts to 100 volts, and this is our portable oil tester. Right, you can see the top view and the connection cord and the earth wire which is you can see in white color that is already connected to the socket outlet as you can see, and then we have our high voltage terminals, right, U and V, which is represented on top of the terminal box, and this is our glass container with two spherical electrodes. Then we have to adjust the initial gap setting of the two electrodes to 0 using the micrometer screw gauge as you have just before seen, and then we can safely fix it to the upper middle part of the high voltage terminals like this. Now we are filling the transformer oil sample up to the red mark line of the glass container. I hope you can see the two marks printed on the glass container. Those two marks which we are interested to select as the threshold value, as the limit, upper limit. For more convenience, we can use a funnel in appropriate size as you can see in this video. That is the most suitable way. That is the most suitable way to pour the transformer oil into the container. After filling the container, then we need to adjust the electrode gap setting according to the requirement of this practical, as you can see. So here our first gap setting is 1.5 millimeters, and again we can adjust it using the micrometer screw gauge as you can see in this video. You can see the rotation of the micrometer screw gauge up to the 1.5 millimeters. Here I hope you can see there is a toggle switch which is nearby the scale, kilovolt scale, source and the trans. Before operating the portable oil tester, we should switch the meter to the trans side. So it's already done. Then we can switch on the gases circuit breaker and the main switch. For this practical, we are operating the tester in manual mode, so we should turn this voltage controller gradually in clockwise direction until the breakdown occurs. So we have to rotate it in clockwise direction like this. Okay, hope you observed the spark and the explosive sound during the breakdown of transformer oil. Now let's see how we can take the measurements of this practical. Since we are using both high voltage terminals U and V for this session, we have to take the readings from the 60 kV scale because it is named as UV scale inside the dial. Here, if you carefully observed, you can notice that the pointer of the meter continuously moves to the right hand side until the breakdown occurs. At the point of breakdown, the pointer stops and starts returning back to the initial zero position. So, as the breakdown voltage, you need to take the maximum value the pointer reaches on the scale before returning. Also, after taking each reading, please make sure to return the voltage controller to the zero position. In addition to that, before adjusting the next gap setting, we must discharge the two high voltage terminals with the discharging rod, as you can see now, to make them safer for us to touch. Now we are going to adjust the electrode gap setting to 3.5 mm for our demonstration purpose. But keep in mind that we have repeat this test for gap spacing from 1.5 mm to 3.5 mm in 0.5 mm steps. After fixing the container properly, please make sure to remove gas bubbles or solid particles if there's any. We'll show you how it is done in the upcoming part of the video. So now it is rotating up to 3.5 millimeters. And tight the screw. So this is how the breakdown occurs for the second gap setting of the transformer oil. You can see now it is in automatic mode. Likewise, we can repeat these steps for the other gap settings as well. Now we are ready to move on to the next oil sample. But before that, we have to follow another simple but essential step. Let's see what it is. So before filling up the next oil sample, we have to clean the glass container properly, because otherwise mixing up with another oil droplets can affect the breakdown strength of the oil sample we are testing. Alright, now we are done with the transformer oil, and next we are moving on to a very familiar oil sample. It is coconut oil. So without any further delay, let's try to find out its breakdown strength. So similar to the previous case, first we have to fill up the coconut oil sample up to the red mark line of the glass container, as you can see in this video. Also please make sure to keep the container in the horizontal plane in order to fill the accurate amount. So as you can see in this video, you have to adjust the horizontal plane properly and pour it up to the red mark. Now you can observe the breakdown of the coconut oil sample for the gap setting of 3.5 mm. Okay, wait, let me ask you something. Did you notice something strange during this breakdown compared to the previous transformer oil breakdown scenario? Hope you did. But if you didn't, let me show you the gas bubble formation during this breakdown. This can happen not only in coconut oil, but also in any form of insulating oil when they go through this kind of breakdown. So now let's go and see how we can remove these gas bubbles. As I mentioned before, there's a separate glass rod for this purpose, as you can see now. Using that, we can remove gas bubbles in this way. Okay, this is the end of the testing for the breakdown strength of coconut oil. Here we demonstrated only for one gap setting, 3.5 mm. But keep in mind, we have to repeat the same steps for other gap settings as well. Now we are moving on to the final oil sample. It is engine oil. But before filling up the new oil sample, don't forget to follow the steps of discharging the high voltage terminals and cleaning the glass container thoroughly. Okay, now let's continue the practical with the new engine oil sample. Alright, now we are ready to pour the engine oil into the glass container. Right, now as you can see, we are filling up the engine oil sample up to the red mark line of the glass container. And also here you can observe we are facing a huge trouble with formation of gas bubbles in large quantities, right, on top of the layer in the liquid. Right, on the surface you can see there are large quantities of bubbles, so we have to remove them as much as possible, otherwise it will affect the breakdown strength of the oil sample. But with the high viscosity of the oil sample, 100% removal of them may not be possible, but we will try our best. So here's the breakdown of engine oil sample for 3.5 mm gap setting. Okay, now we have completed the breakdown strength testing for all three oil samples. But before winding up the laboratory session, we have a small video clip to show you. Hope you remember from the theory part, I mentioned that there can be solid impurities inside the commercial insulating liquids. These impurities can be formed as a byproduct of the liquid through when it goes through the breakdown. Then these newly formed solid particles can either come onto the surface or they can deposit on the electrode surface as small mounds. Eventually, they can cause the reduction of breakdown strength of the liquid unless they are properly removed. Now we are going to observe that kind of special case. Okay, as you have just seen previously in the explanation, by using the glass rod we can remove this. So this is the end of our practical session. Breakdown characteristics of oil. So these are the observations of this laboratory session. Here I have given 6 readings by each gap setting, and you need to take the average of them and prepare another table under the calculations section of your lab report. Then you have to plot 3 graphs, break down voltage versus gap settings for the 3 oil samples, and please make sure to draw them on the same graph sheet for the sake of comparison. Finally, you need to calculate their gradients separately and compare them under the analysis section of the lab report. Later on, you can proceed with the discussion as well.
Alright, this is the end of the laboratory session breakdown characteristics of oils, and hope you received some practical insight about the breakdown strength of different insulation oils with this. So thank you for joining and hope to see you again with the next laboratory practice of semester 7.